Okay, it's that time. Some other people might show up in a bit. Let me. All right, share with you some stuff that you need to know about. Uh, in the Unit 8 folder, that's for the current unit, the current week. It's just the 2 days today. In that folder, there's a few things. These are the gas law example problems that I gave you yesterday and showed you and a couple examples on. I want to go over the rest of these today. And then there's two things that you need to complete. So there's this demonstration. It's called the egg in the bottle demonstration. And normally I do it for you, in person, but it's a video showing a hard-boiled egg. The shell's been removed, and you can put that egg into an Erlenmeyer flask and then remove the flask. And it's a simple problem in gas laws. It's kind of a neat demonstration. So watch the video and then participate in the discussion. Looks like somebody's already done it. And then there's this honors chemistry gas law quick check. And that's not due until April 7th. That's the day when we come back from break. So, I mean, you can do these things today. You can do them tomorrow. You've got until April 7th to get it done. Kind of get it done before we come back. The Where it says honors chemistry gas law quick check, these are some problems that are very much like the examples that I gave you yesterday that we'll go over today. And if you do these problems, then the quick check is actually just the answers to these problems. So it's not as if there's two separate things. This is just the document, and then that is the assessment. It's like a self-grading assessment, but I'll check it because you know how it is. It's like a meme where you put in like 4.0 and it says you're wrong because the answer should have been 4. I'll double check to make sure that uh, something that you put in is like a good answer and whatnot. All right, so these problems, the honors chemistry gas law worksheet with Dalton and Graham's law, those problems I gave you or showed you yesterday. And if you're remote, you kind of know how this goes because you're always, doing stuff online and whatnot. But I did problem 1A and 2 for you. And then, so I'll go over 1B, number 3, 4, 5, and 6. And then the quick check is pretty much exactly the same kind of problems. And I don't know why this is being a little bit slow, but I think it'll work okay. All right, so anyway, I did 1A for you. And then problem 1B, you want to convert this pressure in atmospheres into kilopascal. So you got this pressure in atmospheres. The conversion factor has to have atmospheres in the denominator and kilopascals in the numerator. And this conversion factor says 1 atmosphere is the same as 101.3 kilopascals. Standard pressure is actually 101.325 kilopascals, but that's, good enough. 1 atmosphere is 101.3 kilopascal. Then it's 0.95 times 101.3. Let's see what that comes out to be. 0.95 times 101.3, 96 point. You only have two significant figures because the 0.95 only has two significant figures. So 96 kilopascal. That's what you should have gotten for that problem. All right, we did number 2 together. And then problem number 3, you got a tank. It's got a mixture of gas. It's got some nitrogen, some oxygen, and some methane. So it doesn't really matter. Here I'll draw the tank. So there's the individual tank. You've got a partial pressure of nitrogen of 20.3 kilopascal. And then you have a partial pressure of oxygen that's 32.1 kilopascal. And a partial pressure for methane of 0.05 kilopascal. The total pressure in the gas comes about as a result of the pressures of the individual gases. So this is how much pressure each of the gases contributes. The total pressure is just equal to the sum of the pressures. So if you just take 20.3 and add 32.1 and add 0.05. Now the rule with significant figures, whenever you add values that have different numbers of decimal places, is the answer can only have as many decimal places as whichever the problems have, or whichever the values has the fewest number of decimal places. whenever you straight up add these on your calculator, you should get 52.45 kilopascal. But because the 20.3 and the 32.1 are only good to the nearest tenth, a good answer would be 52.5 kilopascal. And it's not 52.5 because it has three significant figures. In fact, the 0.05 only has one significant figure. But whenever you add values, the number of decimal places in the answer should be as many as whichever the ones has the fewest number of decimal places, and both the partial pressures of nitrogen and oxygen are only to the tenth of a kilopascal. So the answer should only be to the tenth of a kilopascal. You can also calculate what percent of the total pressure each of the gases contributes. And this isn't prompted for in the problem, but if you wanted to know what percent of this total mixture is nitrogen, if you just take the partial pressure of nitrogen and divide it by the total pressure, 52.5, that'll get you some percent. Let's see what that comes out to be. 20.3 divided by 52.5. This is like 39 per, well, we'll just do it with two significant figures. 39% of the gas is nitrogen. The approximate percent of the gas that's oxygen, 32.1 divided by 52.5 is like 61%. And then here, because you take 0.05 and divide it by 52.5, let's see what that comes out to be. 0.05 divided by 52.5. Yeah, this is less than 1%. So it's, let's see, it's 0.00095. So that's like about with, the problem is it's 0% to the nearest 1% because 39 and 61 add up to 1. But with one significant figure, it's 0.001 or 0.1%. So it's about 0.1% methane, 61% oxygen, 39% nitrogen. If you were to carry those out to the tenth place, then it would be, they should add up to right around 100%. So the percent of the gas that happens to be oxygen is just the proportion of the pressure for the oxygen divided by what the total pressure is. Anyway, that's not prompted for in the problem, but that's the way in which you can figure out what the partial pressure of a gas is based upon the proportion of the gas, or the proportion of the gas based upon the partial pressures. Okay, now this is a problem about effusion and diffusion. So the words effusion and diffusion refer to either whether or not it's a gas through an opening or like a pore in a material, or diffusion is the general like spread of a gas in an open volume. And in both cases, it's dependent upon the speeds of the particles, and the speeds of the particles depend upon the mass of the particle. So first off, fluorine, F2, has a mass of about 38 grams per mole, but hydrogen gas has a mass of about 2 grams per mole. So if you had these two particles, you've got hydrogen. Hydrogen molecules are very small, and they're going to have a relatively high velocity or relatively high speed, where fluorine is a much, much larger particle. And at the same temperature, it's going to have the same kinetic energy, but that just means it has a lower velocity. So in the case of these two gases mixed, the hydrogen gas has a much higher velocity, and it's also a much smaller particle. So if you consider each of these two particles, possibly going toward a surface where there's holes in it, or maybe it's like a doorway, not only will the hydrogen gas get there sooner, but the particle size is much smaller, so it's much easier for it to effuse or get through the pores in the material. Where the fluorine gas, not only is the particles larger and moving more slowly, so they're moving more slowly, so there's a lower probability that they'll get to the pores in any amount of time. And then also the speed is slow, or the particle size is larger, so it could be that the membrane is not permeable to that size particle. All right, so which diffuses into a room slower, methane or fluorine? So whenever you find the masses of these, methane has a mass of about 16 grams per mole. Fluorine has a mass of about 38 grams per mole. So if you have a room and both of these gases happen to be in the room, and let's say that the room is just split right down the middle, not as if this ever really happens, and you have methane on one side and you have fluorine on the other, they will mix among each other until there's a pretty equal distribution of methane and fluorine around in the space. But the methane molecules, because they have a smaller mass, have a much higher speed than the fluorine. So you expect the methane to diffuse or spread throughout the room at a much higher rate than the fluorine. So which diffuses into the room more slowly? Well, that's the fluorine in this case because it has a higher mass. Which does effusion faster? It's whichever one has the lower mass, the hydrogen gas. So generally, the higher the molecular weight or the higher the formula mass for the gas, the slower it moves and the longer it takes to get spread out into a space, and the more difficult it is for it to pass through pores in any kind of container. All right, then number 6. So you get some kind of pressure and temperature condition. There's a gas that has some kind of a volume. What volume does the gas occupy at STP? So here's the starting condition. Let's just say this is the gas. Maybe it's a box of gas. Who knows? The pressure starts out as 90 kilopascal, and the temperature is negative 20 degrees Celsius. Very first thing you should ever do is take that temperature in Celsius and convert it into Kelvin. When you add 273, you get 253 Kelvin. So a temperature of negative 20 Celsius is 253 Kelvin. And we know that the volume is 10.4 liters. So this volume is 10.4 liters. What volume does the gas occupy at STP? STP is standard temperature and pressure, and standard temperature and pressure is 0 degrees Celsius and 101.3 kilopascal. So we've got a higher temperature and a higher pressure. So it's not obvious what's going to happen. What I mean by that is because the temperature is 0 degrees Celsius, when you add 273, you get 273 Kelvin. An increase in temperature tends to make the volume larger, but at the same time, the pressure is higher, 101.3 kilopascal, and a higher pressure tends to make the volume smaller. In other words, increasing the pressure would squeeze the gas to be smaller, but at the same time, an increase in temperature tends to make the gas have a larger volume. So it's not immediately obvious what the final volume is going to be. But from the combined gas law, P1 V1 over T1 is equal to P2 V2 over T2. We know the initial volume, pressure, and temperature conditions. We know the final pressure and temperature. We're trying to find that final volume. So when you solve for P2 or V2, it's P1 V1 T2 over P2 T1. The starting pressure is 90 kilopascal, 90.0 kilopascal. The starting volume is 10.4 liters. The final temperature must be in Kelvin, 273 Kelvin. So the pressure and temperature units don't matter so long as they match in the problem, meaning each of these pressures has to be the same pressure. These volumes will be the same volume units, but the temperatures must be in Kelvin. P2 is 101.3 kilopascal, and then T1, starting temperature, 253 Kelvin. So that comes out to be 9.97 liters. You have 3 significant figures, because in all the values, there's like 3 significant figures. Even like, well, the 20 is a little tricky because 20, if you assume that's to the nearest 1 degree Celsius, then this negative 20 and 273 get you 253 with 3. 90.0 has 3 significant figures. 101.3 has 3 significant figures. Well, 0 doesn't really have any significant figures, sort of, but when you add 0 to 273, you just get 273. It's got 3 significant figures, so 3 significant figures is good. This final volume is just slightly less than the initial volume. Here I've kind of exaggerated it, but that final volume is 9.97 liters. It turns out that the ratio of the pressures, which tend to reduce the volume, is greater, or is a like smaller value ratio than the reciprocal of the ratio of the temperatures, 273 to 253. So really that's not anything that's new. It's not a problem related to Dalton's law or Graham's laws, but it's a good practice for doing problems with the combined gas law. Remember, you can always start with the combined gas law too. So in case, instead of having to remember all the different gas laws, if you happen to do a problem where the temperature doesn't change, then all you have to do is just cross out the T's, and then it's P1V1 is equal to P2V2. That's Boyle's law, for instance. Uh, all right, so those are the answers to the problems 1 to 6 from the ones that I gave you yesterday. Like always, the problems are recorded. They're on YouTube and whatnot. I'll put the link on there a little bit later today. Actually, I got to fix the one from yesterday because the link didn't work right and I had to get rid of it. And then I'll fix that in just a few minutes here. So anyway, in the course, you can find it in the folder for this week. There's this honors chemistry quick check. These are additional problems you can practice now. And whenever you get the answers to that, you just complete it in the quick check. So click on the quick check and then do it in the assessment. Also watch the egg in the bottle demonstration and participate in that discussion. So then just as a reminder, on the right-hand side of the course, there's the egg in the bottle demo, and the gas law quick check is like right there. All right. I still have a couple other things I've got to grade. So some people sent me messages or questions about grades. We aren't completing grades until tomorrow. So grades won't be complete until tomorrow night anyway. The end of the marking period's tomorrow, even though today's the last day of the school year. So it's not necessarily true that whatever grade appears in the grade book is like the final grade. Once I get the grades done, um, by Wednesday night, grades will be finished and whatnot. So that's that. If you have any specific questions, you can put them in the chat or whatever, or send me a message or something like that. But I'm gonna get those done like maybe by the end of tonight. We have parent teacher conferences today and tomorrow. So between today and tomorrow, I'll be able to finish reading anything I still have to finish reading. Let's see. Okay, so that's all I have for you today. If you have questions about problems or anything else, you can put it in a chat directly to me. Let's see, missing the mole lab because I didn't find it. I wonder if it's online. The mole lab. Let's see when that was. Hold on, I gotta stop the share. Grade book. So like any assignment has a date and you can usually click directly on it. It'll take you to there's the mole lab for remote students. That is in February 26th. So, I mean, it's not obviously not possible to collect any data at all today, and we're not here. But the mole lab was from February 26th. So that's in Unit 7. If you go into Unit 7, week of 222 to 226, there's a link here that says mole lab for remote students. So it doesn't matter if it's a mole lab for remote students or a mole lab for in-class students. The mole lab for remote students just has data included in it. So you could complete the mole lab because you have to actually like find the masses of those things. These are some samples of masses for objects. You could do the calculations for conversion from masses and volumes into moles using that sample data. Okay, let's see. Any other questions? All right, well, I'll stay on. If you don't have any other questions, That's all I have for you today. Hopefully you have a great break. Hopefully it's relaxing. You have a little bit of fun. Um, Stay safe, stay healthy, and we'll see you in April.